Thank you for introducing me, for the organizer. And I'm going to talk about today the axial green function formulation or axial green function methods for elliptic problems or Stokes flows. This is a recent work in Stokes flow. We have already made some methods which is numerical to solve the elliptic partial differential equations with boundary value, delicate boundary values. For example, the Poisson equation or the other heat conduction problems with variable conductivities. So that's the starting point of the axial green function method. The axial, somebody feels that the axial means the axis of rotation, but in this case, the axial is not the case. So this axial means the just x-axis and y-axis. Okay. So this is quite interesting, I think. Okay. My question is, I would like to solve this kind of elliptic problems. Kappa is some kind of conductivity, and in this case, the right-hand side, if the right-hand side is delta function, then we say this kind of function g is called fundamental solution, or it satisfies the zero boundary conditions, then we say, or we call this function g is the green function. So my question is, can we find, in general, 2D or 3D domains, we have can find the closed form of the green function of elliptic boundary value problems, an arbitrary domain and a given kappa. But in general, it is impossible in a simple domain, even in simple domain. And if kappa is a function, then it is almost impossible to concrete, or we can't find the green function concretely. So, but in 1D case, it is relatively simple compared to higher dimensional problems. And in this case, if kappa is not constant in general, then we can solve this problem always. And the green function g itself is very simple, has a very simple form, and it is closed. If so, my goal is there a way to solve 2D or 3D elliptic boundary value problems using this 1D green function? We call this 1D green function the axial green function. Axial, yeah, axial green function means, take 1D green function only. Yeah, it's not higher dimensional green function, just a 1D green function. So this is very interesting, I think, and it's, in my opinion, this is very interesting because if you know the green function, for example, the direct green function in this problem, then this problem is solved. However, the green function itself is finding the green function has the same difficulty to solve the main problem itself. So that's my question. So, but in 1D problem, this is relatively easy. Okay.
So, let me just say that I really like your sentence, let's make it. This reminds me of what Gilbert one time said that.
Yeah. Okay. Yeah. Yeah, it is well-known 1D green function theory for 1D elliptic boundary value problems. Because it is needed for our future work. So I just brief the theory written here. Okay, this is the conventional or typical 1D elliptic boundary value problems, and the solution is called green function. So it has closed form, looks like this. Here, k is a function of a reciprocal, the integral of a reciprocal of kappa. Okay, this is this can be written in some textbook, Yeah. Okay. The property of a one Lagrange function before has something like this form, yeah, in general. So it is for homogeneity, and to calculate the property in here, this tau is the singularity point. So it is continuous in general, and this continuous derivative occurs at the singular point tau here. So this is just the simple properties of one Lagrange function. Okay, this is another good properties of this Green operator or Green transform like this. This G is the Green function of the problem described in the previous section. So theta is maps L2 to L2, and provided one of copies L2, and theta operator has a good property, transforms L2 into H10 in general. So if pi is L2, then this transform function itself satisfies the general elliptic problems like this. The right hand side is tau. Okay, so this means this Green operator implies the inverse of the differential operator. So I'm sorry. Right. Oh, okay. Yeah. So using the one Green function, we have some representation formula for the solution. If we consider this kind of problems, which is boundary barrier problems of 1D elliptic operator. So it can be easily represent the solution itself with respect to pi, and the boundary values UB and UA look like that. And, or equivalently, we just a simple calculation makes these terms into like that. And we have easily the derivative itself also looks like that. Here, the kappa is assumed to be continuous, and L2, reciprocal function is L2 here. So the stability of this kind of 1D elliptic problems is easily computed like this. If reciprocal of kappa is L2 function, then this is stable. Okay. Then, how can I apply the 1D Green function, simple 1D Green function, to multi-dimensional elliptic boundary barrier problems? That's my first question. Okay, so this is the conceptual diagram of this one. If we have this kind of elliptic boundary barrier problems with the boundary barriers U omega alpha, then we decompose the domain, look like that. Then if you consider some arbitrary point, x bar and y bar, then we have two axial lines. Okay, this is x-axial line, this is y-axial line. So we want to make decompose this operator into two parts. The first part is x and y. So to do so, we introduce some new value pi like that, kappa ux and x. So the second part is kappa u y and y. Yeah, adding these two terms makes right hand side. So if pi is a set in this form, then we just solve this equation. This is just 1D elliptic problems. So you just solve this 1D elliptic problem over here. So you can use, you can represent the solution U in terms of pi on this axial line. And so we have another equation. For example, if it's set like this, then kappa uy and y equal to f minus pi. So we have another representation for like this. This is valid on y-axis line here. So we have two unknowns, u and pi. U is unknown, so pi is unknown. But we have two equations here. So we eliminate these two 1D integral equations. We just identifying the left-hand side on Xc. If Xc is set by x bar and eta is set by y bar, that means these two representations are the same at this cross point. So we just eliminate these two equations. I mean, eliminate this u at this point. So we have
This G is 1D or 2D G, the green function G.
G is only 1D green function.
The one that you
Yes, sure. Yeah, on x-axis line and y-axis line. Yeah, they're basically the same in general. Yeah.
just carry.
Yeah. So we have this kind of I'm sorry. We have this kind of integral equation at x bar here. I'm sorry. Here, cos is cos is x bar, and eta is y bar. I think, in this case. So just the cross point at some cross point or arbitrary point, we have one integral equation. Every point we have this kind of integral equations. So we can solve the pi. This pi is unknown in our case. So you just the right hand side is the unknown. The f is the source term, and here is the I'm sorry. This will be a boundary value over here. So right hand side is unknown. So this pi is unknown. So we make looks like ax equals b. Okay. How about 3D elliptic problems? This is 3D. Then we need two unknown variables. The one is defined on x-axis line. The second one is defined on y-axis line. Then finally we can get the g-axis line equations. The g-axis line equations, the right-hand side will be f minus pi and psi. So we have three integral representations for u. So among three, we reduce just the two integral equations from the three equations. So we eliminate just the u, then we obtain two integral equations for pi and psi. So we can solve that. This is the key idea of the axial Green function method for general elliptic boundary value problems. Okay. I'm a applied mathematician. I'm a applied mathematician or a numerical mathematician, so I'm always focused on the numerical methods. So the Stokes problem itself is a very popular and it's very well-known problems. But please focus on the numerical method itself in this talk. So the typical axial lines, if you consider this kind of domain and some elliptic problems defined in this region, and then boundaries here, we just put the boundary formulation. Then you can just some axial lines and y-axial lines can be made, okay, easily. So this ties in this one. Then on each axial line we have on each cross point here we have just one integral equation here. This looks like that. Then this is x eta is x-axis line and y eta is the y-axis line. Then we perform the numerical integrations of this term and this term. Then we make the ax equals b like that. Then gx plus gy and conceptually pi equal to right hand side f. Yeah. Gx and Gy, these two matrices produced by the first term, this one, and the second term here. So the typical matrix form looks like that. This is sparse because the dot green means the element, non-zero element of this non-zero element of the matrix produced by this integral formulation. So in this case, this matrix is a good matrix. So, okay, there's some computations in detail in digitization of the integral equations, but I will discard that part. And then I move on to the numerical solutions. So in this case, we consider the domain circle or disk in 2D. Then you just make x line here and y lines like that. Then we have cross points between them. And then we compute this kind of problems. The solution itself is a very steep as some curve, and then its gradient also steep at the parabolic curves here. Then it preserves the second order accuracy. Trapezoidal means if you use the numerical integration on 1D axial lines, we use the trapezoidal rule, then it also has second order convergence, and the Gaussian quadrature also produces the same accuracy of order of h square. H means the distance between these two average distance between lines. Okay, this is another example. This is very complicated in general. This is a star-like domain. The axial lines looks like that. This is automatically generated. We just describe the boundary points, put it into the computer, then computer can compute these axial lines automatically. So, and we can solve the elliptic problems like that. Then this is U solution. I think this will be U solution, and this will be derivative of U, and this will be pi, our known pi. In general, pi, the new value of pi belongs to the same space as the forcing term. The dimension has the same as forcing term. So if you consider the right-hand side is L2, then this pi, I believe this pi should be belong to L2 function in general. Okay, this is a spiral domain. Even on randomly distributed axial lines also works in our case. So our method is very stable in general. If you use FDM, then it makes some trouble near boundary. Near boundary, the cross points or axial lines distributed at the boundary points which met with axial lines is distributed very irregularly. Even in that case, it preserves the second order accuracy, but it's not theoretically proved. Just it is made by numerical integration, numerical computation. Okay. Okay. Even in singular cases, singular solutions, we have obtained the synchronized convergence. Looks like that. If the angle pi of alpha belongs to first quadrant, then U solution has a square second order convergence, and gradient U is perfectly order of H. And the second quadrant also H alpha, and then H alpha minus 1 is the derivative of solution error. So at the other cases looks like that. So it depends on the singularity of the solution. I mean, the error produced by our methods are synchronized with the singularity itself. So this is a well-known synchronized error here. This is derivative error, and the solution itself will be like that. Okay. The second goal will be, okay, we successfully developed some other methods like FEM or FDM or BEM. It seems, I think it seems very similar to boundary element methods. However, boundary element methods has blow-up singularity. The Green function itself is blow-up singularity. So you take care of the numerical integration of the boundary. So if the numerical integration is not carefully performed, then you can't guarantee the solution accuracy. Okay? But in our case, the 1D Green function, we only use 1D Green function. 1D Green function has just very weak singularity compared to the higher order Green function or fundamental solution. So it is easily treated. It can be easily treated. Okay. The first obstacle to extend the Axial Green function method to flow problems, it is a system. The previous one is just a single equation. The basic difference is that this is a system. Okay. Then we first decompose this kind of steady Stokes equation into this one. Okay, this is the first two equations is the u component of the momentum equation. Okay, the second part is the momentum equation. The second part of the momentum equation here, just to decompose, just to be introducing pi, we can decompose the first momentum equation can be decomposed into this 1, 2, 3, 4, 5 equations. Okay, the last divergence-free equation is not decomposed. So we have 5 equations. But 2 unknowns newly introduced. So we have 5 unknowns and we have 5 equations. Later on, we just eliminate u and we can reduce just 3 equations. Here, the unknown is u. U has 2 components in general in 2 dimensions, and p is another unknown. So we have 3 unknowns. So we can reduce this system of equation into 3 equations in terms of in terms of pi and psi and pressure p. Okay, that's the key idea. This decomposition is key idea, one of the key ideas. I mean, if you have another better decomposition, then you can just apply this AGM method more efficiently. But in my idea, this is my limitation. I just I can think only one candidate, but this is very successfully produces successful results. Okay, this is a revisiting of the axial lines and y-axial lines. So we use x-axial line. We define the x-axial Green function like that. This is y-axial Green function. So the same. In this case, there is no kappa, so only Laplacian. So the conductivity kappa is only 1 in this case. So the Green function itself is can be reduced, very simple form, like that. There's no integration. Okay, here. So these two are very similar to the reference Green function in 1D problem. You just enlarging this one. in writing this Green function, okay, I'm sorry. A Green function, this can be translated to these two Green functions. Okay. The other stuff is very straightforward. If you decompose the operator itself to actual operators, so we need this kind of a property. The one-D Green function with respect to the derivative with respect to t has Heaviside function, and the second derivative part has also Heaviside part. If you define the boundary operator like that, boundary due to the boundary values, and we have this kind of four representations. Well, this is quite similar to the that in the elliptic problem. Okay. Okay. We just integration by part here. Integration by part, the px part here. Then we can obtain these four sets for integral equations. So eliminate these two terms. I'll eliminate u by using the first and second equation. We can eliminate this one only at cross points. Okay? We can also eliminate v only at cross point. So we have two integral equations like that. Pi, psi, and psi. Here there's another variable p. P is the pressure of the Stokes equation. So we have three unknowns, pi, psi, and p. We have two integral equations. So we need one more additional equation, which can be derived from the divergence-free condition. Okay. You could see, you can be represented by the axial Green function. So we just derivative directly of the solution u itself. Then we obtain this kind of formulas. So just here, Heaviside function. Then if you can see this term, there's some delta function here. So we extract the p itself into outside here, like that. Okay. The Vy, this means Vy. The first one means Ux. So Ux, Vy, the addition of these two terms must be 0 because of the incompressibility condition. So we have this kind of incompressibility condition for steady Stokes prose. In this formula, it is very useful because P is explicitly located outside the integral sign. So the pressure P can be represented by pi and psi explicitly. This is very useful formula in numerically or theoretically, I think. Have you ever seen this kind of explicit formula for pressure and velocity or other variables? To my knowledge, this is the first one, I think. Okay, so we have three integral equations. The last one is divergence-free, and the second two comes from the momentum equation. So we have unknown p, psi, and pi. So this is just the algorithm how to solve the pi and psi. The Pn is given here, the previous one. Then solve x momentum, y momentum equation. And then we update Pn plus 1 using the previous Pn psi n, which was solved previously. Okay, the final form of the Stokes AGM formulation looks like that. In general, if you use FDM or FEM, except for the penalty method, if you use penalty method, the last three submatrix is not zero for if you're using the penalty method. But the other methods, this will be 0 always. So that makes some problem. But in our case, this will be very good. Matrix is located the third part of the Stokes system. So this is the main merits of our methods, main advantage. So the right-hand side looks quite complicated, but it's not complicated because this is forcing term the transformation by using green function. These comes from boundary values. Okay. So we use the basis functions for axial line, on each axial line. This is x-axial line, y-axial line. So we just the approximation function like that. This is a FE approximation on 1D problems. Okay. These are numerical results. This is inclined partial flow. If you flow, there's some inflow here, outflow here, profiles, whose profile is a parabola, which is called partial flow in general. But we incline partial flow. The purpose to take this example, then you can see the irregularly distributed boundary point here, over here, over here. So this one is not regularly distributed x-axial line, y-axial line case. So in this case, we have very good convergence results. Even in this case, we have also the second order, and directive and pressure is a first order convergence. Okay. This is a reed-driven cavity flow. How much time do I have?
Around 10 minutes.
10 minutes? Okay. This should be checked if you develop some numerical methods always. So I also checked this example. This is a kind of benchmark problem for numerical methods. So this is U velocity and V velocity. This is pressure. There's some deep singularity here, and this is streamline data. Here, the center points will be, in our case, 0.7633. So this is quite accurate compared to other results. Okay. The second example will be flow around the circular cylinder. Okay, there's some duct here, duct or tube, 2D tube, and inside some circular cylinder like that, circular cylinder, 2D circular cylinder here, and this is duct like that. So the left boundary, on the left boundary, we assign the parabolic, the parabolic shaped velocity, U velocity, and exit, the same prox should be given here. Then the flows must be have the figure like that. Okay, so this is the zoom-in view over here. So can you see this point? There's irregularly distributed points. So we have very good results like that. U velocity, V velocity, pressure, and vorticity. This is quite good agreement to other results also. This will be, if you look at the circular cylinder a little bit down to the previous one, like that, then you have this kind of situations. Then even this will be exactly attached. The circular cylinder can be attached to the wall, bottom wall. Even in this case, we have very good computation results here. Okay, the other one will be, the previous one is a regular flow, but in this case, the singular flow occurs. This kind of singular geometry. Can you see here the horizontal slit here with the length 1, and also the same inflow and outflow like that. Then if you zooming in this region, then it can be shown like that. Here, there's some adaptation here, So this can show our methods is very free to the axial line distributions. Okay, so this is U velocity here. V velocity looks like that. Here is singularity, and pressure has some singularity like that. Vorticity also has the singularity like that. In vorticity, yeah, can you see the blue has a large values, and red is very low values. So over here, it has a perfect discontinuity in this case. Okay, this is vertical slit. Also, we have this kind of numerical results. This is vorticity. In this case, the vorticity is continuous across the slit. But in this case, pressure has discontinuity near the slit. Okay. So this will be inclined slit. Oh, we have this one. This is Mopard eddy. Okay. In Stokes flow, Mopard eddy effect is a very famous one in general. Mopard eddy can occur if we make some disturbance at the pocket of some Stokes flow region, and you have just some kind of Lipschitz wedges. Then at the pocket there's some disturbance. Then Mopard can show theoretically there's infinite eddy take places towards the vertex of the wedge. So it can show the eddies like that. Eddies appear here, big eddies appear here, and appear here, here, here. So we have 1, 2, 3, 4, 5, 6. We can catch up with 6 vertices using our method. The last example would be the Stokes flow in very complicated domains. So this is, in some sense, it looks like a circulation system in our body. So this is capillary in some sense. This is miniature. And even recently, many people are interested in the laminar chip. There's a small channels over here on some glass. Then put some fluids or put some particles into the laminar chip. Then it pulls, and there's some mixing of there, and there's a separation occurs. So finally, we can detect some particles or some other chemicals. So if you analyze such kind of a very complicated flow, we can show our methods is very suitable for such kind of flow problems. So there's inflow here, there's outflow here. Then what happens in this case? This is U velocity here. There's a strong velocities put in into the this stop, and then it flows out at the outlet here. Then this is V velocity. Okay, the V velocity is very high in this field. U velocity is very high in this field and very low there. There's almost zero because U velocity is right hand side. Okay, it towards the right direction like that. This is pressure, and this is vorticity. Okay, this is final figure. In this case, flows through this line. This is a streamline here. This is a kind of flux. Okay, the two are the same flux. This is inlet flux and outlet flux. So if we compare these two branches, this tube bifurcates. First bifurcates here, and bifurcates again in this part, and they merge together here, merge together here. Again, they come all together in this place. So these two channels, can you see here? This prox is bigger than this one. So the fall prefers to fall in this channel. Okay, so there's a fourth channel here. So the maximum prox occurs the second channel like that. Okay. The last one is pressure. The figures of 3D plots of the pressure. This is inlet and this is outlet. Inlet here, outlet here. So pressure has some distributions like that. Pressure gradually decreases here, 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 here. Okay, we can show that. Okay, thank you very much.